All right, so welcome back, everybody. So now we go to another part. So as I said, this is actually good news, right? What we've done so far is pretty much the bachelor's level of information retrieval, right? So we have already seen everything that is typically taught in universities at that level for information retrieval. The book actually also has advanced contents, and so I also picked a few things that I think are very interesting. Two actually. The first one is the probabilistic information retrieval, and the second one is with the language models, which is yet another approach to information retrieval. So basically what's going to happen is that today and next week and the week after that, we are just going to explore this master's level content, right, on these other approaches. And that's pretty much it, right? But first, of course, as I said, congratulations, because we are done with the bachelor's level contents. Okay, so I like to have a quick recap, right? So we've seen Boolean retrieval where we have an input collection, a Boolean query language, and here we do not rank, we just take a subset, right? Then we looked into ranked retrieval, where we have the queries that are more in free form like that. And then we have a ranked subset of the documents in the outputs. And now we are looking, so to say, at a third way of looking at things. Now, before we do that, I want to make sure, because as I said, it's master's level, so that's of course going to be more complicated. It involves a lot of probabilities. Now you had probabilities lectures, right? Probability and statistics and so on, but I just want to make sure that it's really on the front of your mind, right? So I'm going to have a recap of probability theory, and then we'll apply that to information retrieval. Okay, so probabilities, right? So it's something that we have been doing for thousands of years, but the best, I think the most common formalization that there is to it is that we have some omega space, so typically uppercase omega, that is basically the set of everything that can happen, right? More exactly, this is a set of what are called elementary events, right? It can be millions or billions and so on, can even be infinite. But every element in there is one possible, let's call it, state of the world, right? So this is what we start with. And here is an example where I have now an omega with 5 elementary events, right? 5 of them. And what happens next is that I introduce, it's called a measure. That's the fancy term. Actually, it's also, it can, it's very interesting. It's a subfield of mathematics on its own, right? The measure theory. But basically what it's about in the discrete case that is just points, it's just a few numbers between 0 and 1 that add up to 1, right? And then you have a probability. This is just a measure on the omega space, right? So I just put the math in there, right? So it's P is a function from the omega space to numbers between 0 and 1 that sum up to 1, and I call it P of omega, right? I might alternate between uppercase P or lowercase p, but don't put too much attention to whether I put it uppercase or lowercase. All right. And once you have this function P that assigns the weight to every elementary event, what's happening is that we can define events like this that I call E. So this is an event, and an event is actually a subset of omega. Right. So, for example, an event can be it's raining on May 2nd, or it's sunny on that or that day, or I have my umbrella, or I am right here in the lecture. So an event is just, you can actually use an English sentence for it. It's something that might or might not happen. And then the idea is that an event consists of plenty of elementary events, right? So maybe this is, if the event says it's raining, maybe this is it's raining and I have my umbrella, it's raining and I don't have my umbrella, right? And many other possibilities. So you see why this is defined as a subset rather than an elementary event, right? So the elementary event is really the most fine-grained, I would even call it deterministic state of the world that you can have. and then you define an event as a subset, right? And once you have an event, you can define the probability of an event, and it's very intuitive. You just add the weights. You just take all the weights that are in there. So 2 + 2 + 1 gives you 5, right? So you add them, and this means that the probability of E in that case is 0.5, right? This is really just a recap. So I'm assuming you already knew that, right? Okay, so great. So then we have the complement, right? Where you usually put the horizontal bar. There's also a notation with a small c that you can use. So the complement is just the set of all the elementary events that are not in the original event. And of course, the probability is 1 minus, right? If there's a probability of 40% that it rains, then there is a probability of 60% that it doesn't, right? So it's 1 minus. Okay, something else, we use it actually, probabilistic information retrieval, is called the odds. What are the odds? Well, it's only an alternate way of looking at probabilities. In fact, it's the way that if you go to these locations where you can bet on horses, or there are, in some countries it's very popular, right? You can bet on the first name of the future prince, or and so on and so on. So the way it's done is not in terms of probability, it's in terms of odds, like 2 to 1, 3 to 1, right? And the way you compute an odd is just the division of the probability of the event divided by the probability of its complements. It's quite intuitive, because basically if you have an event that has a probability of 50%, 1/2, then the odds are 1 to 1. So 1 to 1 is really, you don't know, it's 50%, 50%. If you have 2/3, 1/3, so if there's a probability of 2/3 that it's raining and 1/3 that it doesn't, then the odds are 2 to 1, right? So the odds is really just that. It's when you compute the ratio of the probability divided by the probability of the complement. All right? So these are the odds. Next, as we have the events that are actually sets, because they are subsets of omega, then we have everything we can do on sets: union, intersection, complement, we've already seen it. So now I can define 2 events. For example, E is it's raining, F is I have my umbrella. And this event right there, the 0.1, it has both of them. It's both raining and I have my umbrella, right? It turns out there's only one elementary event, but of course there could be more in the intersection. And then you can, of course, also decide, because that's also an event, it's also a set, so there's the probability of the intersection. But all you can say is that that probability is between 0 and the minimum of the probability of E and F. That's all you can say, right? Because, of course, there's a lot of freedom in the way that the intersection can be organized. All right, and then you have the union. So here it's raining, or I have my umbrella, and this is everything in there, right? And actually, you already have an interesting formula in there that basically says that if you want the probability of the union, you add the 2 probabilities of E and F, but then you counted that twice. So this is why you need to subtract the intersection, right? And this is also a fundamental formula in probability theory. Okay. Now there is a special case in which the intersection is empty. This is called disjoint events. In that case, they don't even intersect. It's like it's raining and I was saying it's raining and it's sunny, but no, it can actually happen both at the same time. It's snowing and it's 40 degrees. Okay, then I'm sure it doesn't happen at the same time, right? So then there is no intersection in there. What happens is that the probability of the union is just the sum of the 2 probabilities. Okay. Then another rule is called the partition rule. It's that you can decompose the probability of an event, given another event, into that part and that part right here, right? So it's just the sum of the 2. So this is the probability of E and F. It rains and I have my umbrella, or it rains and I don't have my umbrella, right? So you can, that's kind of a decomposition, right, for the computation. All right. Next, because it gets more complicated, of course, we build more and more complicated things. A conditional probability. A conditional probability, for example, E condition on F, the visual that you should have is, it's as if, there's omega, and then we shrink omega to just be F. And then we recompute the probability of E, but within this smaller omega. this is actually a Bayesian thing to do, like in Bayesian networks. It's the idea that you learned some information. For example, it might have been that I'm looking at whether it's raining or not, and then I give you the information, okay, I have my umbrella. Then you know you're in here, right? So then you have to recompute the probability in there. And of course, you need to renormalize, right? You need for that to sum to 1 again, right? So this is the Bayesian reasoning. And so the way it's computed is very easy. It's really the probability of the intersection, but you renormalize it with the probability of F, because as I said, this is kind of the new omega, right? So this is the new possible set of possible events. Okay. So this is the visual, right? So Bayesian reasoning, I give you information, and now this is my new universe of possibles, okay? So I adapt my probability in that way. Okay. Then that gives me my chain rule, which means that you can compute the probability of the intersection as the probability of F, that I have my umbrella, multiplied with the probability that it rains, knowing that I have my umbrella. This is called the chain rule. This is also absolutely fundamental in Bayesian reasoning. It can also be 3. No, that's something else. This is called the chain rule, and it's fundamental in Bayesian reasoning, right? Okay. Then there is a special case where it turns out that F doesn't teach you anything. I'm telling you I have my umbrella, but there's no information in there. So basically that means that the probability of E knowing F just remains the same. It's still the probability of E, right? So you didn't learn anything with F. What that means now, if you apply the formula of before, is that the probability of the intersection is the product of the two probabilities. Now it's something familiar. It just means that two events are independent of each other. Right. And then you multiply. And again, in combinatorics, when you actually calculate things, like for example, you have a sequence of coin tosses, right? And every coin toss is independent of each other. You know Bernoulli trials, right? Then you just multiply, 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 right? So this is the special case in which events are independent. So again, do not confuse the two. Independent means you multiply. Disjoint means you add, right? Disjoint is an addition. Independent is a multiplication. Okay. So now that we have everything, here is a puzzle. When it rains, I forget my umbrella 5% of the time. Maybe it's based on the previous years. The other information, maybe from Meteo Suisse, Meteo Schweiz, it rains every other day. That's another piece of information. Last year, that's the third information, I had my umbrella on 271 days. And what I want to know is, since I have my umbrella to date right there in my bag, is it raining outside? How do you do that? How do you solve that? Looking on Zoom too. How do you solve? So even if you don't give me the computation, at least let's say what formula or what approach would you use to solve this puzzle? Yes?
The umbrella when it rains. Therefore, we have P of, we would have P of like not having you like P of U knowing like P of like not U knowing R.
Yeah, so let's call them U and R. Yes, absolutely. So the P of U, the complement of U knowing R, yes.
It rains every other day means that R is 50%.
Yes, so that's the probability of R.
And therefore, we know we can just use the mathematical. That's right. Just like
yes, so you can multiply them, right? This is what you're saying.
Yes.
This is P of R multiplied by probability of not U given R. That gives you the probability of not U. Yes, and then?
Last year, my umbrella. So since we know that we didn't have it on 200.
So sorry, I made a mistake. That's the probability of not U and R.
Yes.
When you multiply. So the probability of not U and R.
And then we need to calculate out not U and R. And then
You're almost there. You're almost there.
I know, it's just interesting. Because I can't write, so.
Yeah, of course, it's much harder when we just speak, right? But we are doing it together. So no worries. We are doing it together. So we have the probability of R and not U, right? So I can conclude the probability of R and U, right?
Yes.
Just the complement within R. So I have the probability of R and U, and I have the probability of U.
R and not U.
And what am I trying to compute here?
The P of U, basically. Oh, sorry. P of R knowing
U.
like knowing.
Exactly. So we want the probability of R knowing U. And we have the probability of R and U, and we have the probability of U. So what operation do we do?
Well, we do the mathematics, right? We take the P of R and like U and divide it by P.
Exactly. Yeah, we divide.
Of U.
Yeah, that's it. We did it. You see, so it's just really multiplying, dividing. So we do the math, and then we have the probability, the conditional probability that it's raining given that I have my umbrella. So we can have a visual representation of what we've just been doing right here, because the reasoning is correct. So the idea is that I have here that the probability that I have my umbrella given that it's raining. That's the probability that it's raining given that I have my umbrella. And I give you the probability that I don't forget my umbrella if it rains. The likelihood that it's raining if I took my umbrella. And we basically computed this probability of R and U, right? So with the multiplication. All right. So there is a name for that, for what we just did actually. So we use the chain rule, right? The probability of R and U, which is the multiplication of that. We can also use the chain rule the other way around, right? So this we have, this we have, this we have. We are looking for that. But if we write the chain rule twice, just swapping the two events, what we get is this. The probability that I have my umbrella given that it rains is the probability I have my umbrella. Sorry, let me start again. The probability that it rains knowing I have my umbrella is the probability of the reverse, that I have my umbrella that it rains, multiplied by the probability that it rains, divided by the probability I have my umbrella. What is this called? Well, it's up there. It's called the Bayes formula, right? So this is the heart of Bayesian reasoning. This is extremely powerful. It looks like a trivial formula. It is extraordinarily powerful. There's the whole, in statistics, you know, the causal models, they are based on Bayesian networks where you have a whole graph of events. It's popular, for example, in medicine. You know, we talked about it in the previous years, right? The efficiency of a vaccine and so on and so on. And this can all be modeled with Bayesian networks, this sort of reasoning. And yes, during the pandemic, it was something that was repeated because this is not very intuitive. But when you consider the probability of having a severe case given the vaccine, not given the vaccine, and so on, in fact, it's the Bayesian formula that you needed to apply in order to get the actual numbers. All right. So this is the Bayesian the Bayesian approach to probabilities. And what actually happens when you have a Bayesian reasoning is that you basically can express a probability, a conditional probability, with some magic in terms of the reverse one. And what actually, the reason why we actually do that is that typically it can be very, very easy to compute that one, but it's very complicated to compute the other one. And this is why the Bayesian formula basically gives you the bridge between the two. So now you can just plug all the values in, and then you can have this result of 60%, that there's a 60% likelihood, we prefer to say likelihood than probability, that it's raining outside, right? And so, of course, this implies that the semantics that you have in mind for probabilities here is not an absolute semantics like you would have in quantum physics, right? That there is an actual randomness. It really has to do with you as a human being making assumptions about the world. And you just have information that is flowing in and that accumulates and that allows you to update your estimates of whether or not something is going to happen or not to happen, right? So this is thanks to the Bayes formula. So I have plenty of visuals here, but this is really pretty much it. I had my umbrella 271 times on these days. I only forgot it 5% of the rainy days. It rains 50% of the time, so this gives me the areas, and it rains 64% of the time on the day that I have my umbrella. So you see now, this is called the prior. This is the a priori probability. There's a node of 1 to 1 that it rains. But if I give you the extra information, I have my umbrella, then it jumps to 64%, right? Just got a little bit higher. Because of course, that's a hint. If I have my umbrella, that's a good hint that probably there's a reason for it. All right, so I'm repeating, but this is very important. This is the prior. And then we update it with this multiplication and division, and we get the posterior, right? So this is before the information, after the information. Okay. And here I do it again. This is the Bayes rule, right? Where you have the probability of E given F computed with where you swap the sides right there. Okay. So far, so good. It's going to be very useful, right? I'm going to use that in information retrieval, but again, this is just information that I will need. Is everything clear? This is something you should already know, right? Then we have random variables. Random variables are actually functions that associate every elementary event in a target set. So for example, my random variables could associate shapes and colors, right? So I have a target set S, and it's really a function that goes from omega to S that associates every elementary event with a value. And when I have that, I can derive a probability distribution no longer on omega, but on S. Right. So now I can forget about the elementary event and just focus on S. And the way I compute that, it's very intuitive, right? The probability that the value of X is a specific value, small x, it's just the sum of the weights of each elementary event that gives me that value. For example, the probability that my shape is a blue square is 0.4. It's the sum of these two. The probability that it's a red pentagon is 0.1. The probability that it's a green rectangle is 0.5, right? You just need to add together all the elementary events that give you the same value, right? So it's very important to understand that a random variable is really a function. That's what it is. So you should not confuse a random variable with a mathematical variable. It's not the same thing. And that's why, unfortunately, in many textbooks, they do not really do that, which is sad because pedagogically it makes it harder to learn, right? But I try to stick to the convention that my random variables are uppercase, big X, that's a random variable, and the actual possible values it can take, lowercase. I'm going to do that through the entire lecture that I'll continue next week, right? Uppercase, that's a random variable. Lowercase, that's one possible value of my random variable. Okay, so, okay, this is what I just computed. And typically what people do when they use random variables, and this is what researchers do when they use that, they forget about omega. They kind of drop omega. It's like when you learn a bicycle and you remove the little wheels, right? So you basically just stop looking at it and just look at the random variables. So this is why in many textbooks or many disciplines or many lectures, you just deal with random variables and never with elementary events. But nevertheless, it can be very useful to remember that there is actually an omega behind the random variables and that these are really just functions. Okay, so I use this notation for the derived probability distribution on the values of the random variable. You can also write it that way, right? So either like this with p subscript x, and then that takes one of the possible values of the random variable, or you can write it as the probability that big X, the random variable, equals a specific value. The probability that big X is the blue square, the probability that big X is the pentagon, and so on. And actually, that makes a lot of sense this way as well. Because what is this? That's an event. This here is just the subset of omega, such that X of small omega is the blue square. So this is why this notation is fine too. However, and I'm going to finish on that today and start again next week with that, do not ever do that, ever. Because this, unfortunately, people do it. In the textbook, unfortunately, they do it as well. But this is very, 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 very bad. It's ambiguous. You don't really know. I mean, it's approximating what you're talking about. Never do that. When you see that this is done, always try to reconstruct the intent behind that. Right. So this is really this way or that way. These are the two acceptable ways. Do not write it like that. So that means that they basically take the probability function, the original one, that's supposed to take a small omega, and the parameter they give it there is the value of the random variable. And this is why it's mathematically inconsistent. Right. Okay, so now you know, do not ever do that. Okay. Of course, once you have your master's degree and you are a PhD student or a famous professor, you can do that absolutely if you know what you're talking about, right? But until you have your master's degree, do not do that. Okay. I still think that people who teach to bachelor's and master's students should also avoid doing that for pedagogical reasons. Okay, so I'm very glad that I finished with that, because that way I'm sure that you remember that message. So it's really good. Okay, so I'm going to stop here. So thank you very much. Next week, so I'll finish on that, and then we'll use that, all of that, we'll use it for information retrieval. We'll see that we can derive a very powerful information retrieval system just with Bayesian formulas and random variables. So I'll see you next week for that, and I hope you'll enjoy it. And okay, so enjoy the exercise session, and see you. Goodbye, everybody.